Hi everyone, welcome to our webinar today. My name is Justin D'Souza. I'm a statistician and quantitative specialist here at Statistics Solutions. During today's webinar, we will be discussing a breakdown of different regression models. If you have any questions, please type them into the chat box. I do have a colleague of mine, Isades, who will be assisting with questions. And if we have any additional questions, I will answer those at the end of the session today. Okay, so today we will be discussing the services that our company, Statistics Solutions, provides. We'll be discussing 3 different regression types. Then I will show a demonstration of our Intellectus software, and we will continue with the summary. Okay, so Statistics Solutions provides assistance with nearly every portion of the dissertation process. So the way our company works is we will assign a methodologist specialist to you, and we'll also assign a literature review specialist to you, depending on what chapters that you need the most assistance in. So starting with topic development, going through the proposal, IRB forms, data entry templates. We can host your SurveyMonkey survey for you. We have our own SurveyMonkey account. We help with both quantitative and qualitative dissertations. We help with the discussion chapter, PowerPoints for defense, and journal publications. So let us know if you need assistance with any portion. Maybe you've hit a roadblock. Let us know specifically what is the hurdle for you, and we can assign the specialist to you to help expedite the process. At the bottom here, you'll see a number that you can contact for a free consultation in which you will speak to our sales team, and they will determine the best package for you, and they'll give a demonstration, or they'll give an explanation of how we can provide the most assistance. For today's topic, we're going to discuss the different linear regression types, or different regression types, I'm sorry, linear regression being one of them. So we have 3 different regression types, and we'll break it down to what type of dependent variable you need to run these analyses. We'll discuss what type of independent variables you need. We'll touch on assumption testing, and we will discuss how to crunch those numbers in Intellectus, which is our company software. Okay, so a regression is a statistical analysis that tests the relationship between a predictor and a criterion variable. The key word for regression is predict. So it's always when you're trying to predict an outcome. Now, an independent variable is synonymous with a predictor, and a dependent variable is synonymous with a criterion variable. When you do a regression, the typical terminology you'll see will be predictor and criterion. So the 3 types of regression analyses are linear regression, a binary multinomial logistic regression, and an ordinal logistic regression. The choice of which regression model you run is dependent on the level of measurement for your dependent variable or your criterion variable. If you have continuous data or interval ratio data, you're going to run a linear regression. So continuous data is kind of like anything that is falling on a scale or falling on a continuum. Measurements like height, weight, BMI, age. If age is like you're giving a survey and you're asking for a specific age for each participant, data like that is numeric and can fall on a range is continuous. A good definition or a good a clear example of a continuous variable is when you have a decimal value, 2.6, 5.8. Whenever you have a decimal, it's most likely going to be a continuous variable. A logistic regression, and specifically a binary or multinomial logistic regression, is used when you're trying to predict a categorical outcome. So categorical, if you're doing a binary means there are two possibilities. So maybe passing and failing of an exam. Maybe you're trying to predict gender, if gender is only male and female. Multinomial is used when you have three or more possibilities for your outcome. Something like ethnicity would be a multinomial example if you're trying to predict ethnicity, meaning white, Asian, Black, Hispanic, something along those lines. An ordinal logistic regression is used when your dependent variable is ordinal. So if you're using a singular Likert scale response question, maybe from strongly disagree up to strongly agree, that one item is ordinal on its own. Maybe education level would also be considered to be ordinal. If you go from high school, bachelor's, master's, doctorate, ordinal has a hierarchy to it. So it goes up a ladder in a sequential order, but it's not continuous because it's not really numeric. It has categories to it that go up in order. In terms of the predictors for your regression models, the same definitions apply. You can use any level of measurement for predictor variables. You can have continuous variables, you can have nominal variables, and ordinal variables as predictors. So I kind of touched on this in the previous slide. What does continuous, nominal, and ordinal mean? And I give examples here. So continuous data, again, falls in a continuum. It's a scale. It can be test scores, temperature, weight. Very common that's used today would be composite scores. So if you're using a survey that's measuring a construct, like say job satisfaction or self-efficacy, and you have a series of Likert scaled items ranging maybe from 1 to 5, strongly disagree to strongly agree. Once you take an average or a sum of those individual Likert scale items, that new variable becomes continuous. So that's a very common use of a linear regression when you're using a dependent variable that is built on Likert scaled items. Nominal variable, like we discussed, are variables that have 2 or more categories, but they don't have an intrinsic order, such as gender, ethnicity, or passing and failing of an exam. It's a dichotomous response there. An ordinal variable is similar to nominal. It's actually a subset of a nominal variable, but the categories can be ranked. So I mentioned previously, education level is ordinal, or individual Likert scale items on a survey. So say you have these 5 possibilities, 1, 2, 3, 4, 5. This would be considered ordinal. In terms of coding for your regression analysis, no adjustments need to be made for continuous data or continuous variables. You just input the variable as it is into the regression model as it is coded. If you're using a dichotomous predictor, such as passing and failing, typically you need to code the absence of your condition as the lower value. So say you're doing a regression and you're putting in the result of a test. Did they pass or fail? Typically, the fail is going to get a 0 and a 1 will be a pass. That makes it easier for interpretation when you get to your regression model. In terms of a categorical variable with 3 or more groups or an ordinal variable, you are most likely going to need to dummy code your predictor variables. So dummy coding is used when you have categorical data. When you put these variables into a regression, if you just put ethnicity into a regression model, it doesn't understand what those different categories mean. So we have to assign meaning to these different categories. And the way this works is you assign a reference group for your variable. So typically, in my experience, I've seen if you give a survey and such as race or ethnicity, you use the most prevalent group as your reference. So in this example, we had 5 possibilities for race. When we dummy code, we are essentially creating 4 new variables, and we're assigning white as the reference group. So black would be versus white, Asian versus white, Hispanic versus white, and other versus white. So you'll always have, based on the possibilities, you'll have 1 less total dummy coded variables. There were 5 possibilities here. Subtract 1, you're going to have 4 dummy coded variables. It would take 30 minutes for me to explain dummy coding in its entirety. So I would recommend checking out YouTube videos that kind of explain the process, how to dummy code manually. SPSS, you can even do it automatically if you just assign a reference group, or even just Google how to dummy code. And there are hundreds of articles on that process. In terms of the process for interpretation, the first thing you want to do once you've run your regression model is check for the assumptions. The parametric assumptions of the analyses need to be met. Now, linear regressions have far more stringent assumptions to check in comparison to logistic regression models. And that's because you have a continuous dependent variable. The 3 key assumptions to check for a linear regression are normality, homoscedasticity, and absence of multicollinearity. So normality is making sure that your data follows a bell-shaped curve. That's typically checked with a normal PP plot or a QQ plot. Homoscedasticity is making sure that the residuals are randomly distributed. So you need to check that with a residual scatter plot. And typically in this plot, you want to see just an absence of a pattern. You don't want to see a straight line. You don't want to see an exponential curve. You just want to see random scatter. The final assumption is absence of multicollinearity, and that's checking to make sure that your predictor variables, if you have multiple predictors, you want to make sure that those are not highly correlated with one another. And you check that. There are many ways to check that. You can just run correlations between your predictors. That's one way to do it. And ideally, those correlation coefficients are not too high. The other way to do it is to look at variance inflation factors, which are very often part of the output for a regression model. And then you just examine those VIF values, variance inflation factors, and you make sure that they aren't too high. So for a linear regression, you would check all 3 of these. For a logistic regression, you would typically only check for absence of multicollinearity. So it can be daunting when you're running a regression model. You're like, what is all this random information? Where do I start interpreting? It is intimidating, but it can really be broken down into 3 steps. You first want to interpret the omnibus test, which is really the collective model. Does the collective model appear to represent a linear relationship, or a significant relationship, I should say? And you do that by looking at the f-test or the chi-square test, and ideally you have a p-value less than 0.05. If that step is true, then you continue. You still do step 2 regardless, so you need to interpret your coefficient of determination. That will tell you whether, it tells you how much variance in your outcome can be explained by your predictor variables. So if you're doing a linear regression, you use an f-test. If you're doing a logistic regression, use a chi-square test. If you're doing a linear regression, you also use just a characteristic r-squared. And if you're doing a logistic, you would interpret the McFadden's r-squared, which is sometimes called an alternate to that as a Nagle-Kirke r-squared. So if step 1 is significant, then you go to step 3 here. If step 1 is not significant, your omnibus test is not significant, you pretty much stop right there. You just say, we did not find a significant collective regression model. Therefore, you don't examine each predictor variable. If step 1 is significant, your omnibus test is significant, then you go to step 3 and you interpret the strength of every predictor in your model. So if you're doing a linear regression, you interpret a t-test. If you're doing a logistic regression, you interpret a chi-square test. And if a single predictor is significant, then you interpret the coefficients. You would interpret, for a linear regression, the unstandardized beta coefficient. And for a logistic regression, you interpret the odds ratio. Okay, so 3 steps. Step 1, if that's significant, then you go on to step 3. You interpret step 2 regardless all the time. If step 1 is not significant, you pretty much stop there and you can't reject your null hypothesis. Now we'll go ahead and do a demo of intellectus statistics. So this is what intellectus statistics looks like. What you can do first is you can upload a project. So if you have a data set in Excel or SPSS or SAS, you can create a project right here. Call it webinar December. So you can really enter your data in the software manually. You can upload it through a URL or you can upload a file. So if I go to file, then it gives you different possibilities for uploading the software. The most common would probably be Excel, CSV, or SPSS, which would be a .sav. So I'll go ahead and click that. We need to find this file on our computer. So I have an example here. Upload file. And once that is done, you will see a breakdown of all the variables in your spreadsheet. And it automatically assigns a level of measurement for each variable. So if you have categorical data, such as race or gender, it's going to identify those as nominal. If you have interval numeric data, it's going to be scale. So this is what the data looks like. I'll show you an example of each regression, but before I get to that, I just want to show you some of the options on the left here. So we allow you to edit data in here. So if you need to manually change anything, you can do that. You can reverse code items. So if you have from strongly agree to strongly disagree or a Likert scale, but you need to reverse that for interpretation because you have a negatively phrased question, then you can reverse code items. We have imputation to replace missing values. You can remove univariate and multivariate outliers. That might be, depending on what reference you read, that might be one of the assumptions to check for a regression. You can create composite scores using the variable calculator, and you can download your data into a CSV format, right? That's kind of like Excel. At the bottom here, we have a decision tree, which if you're kind of at the methodology phase, you can figure out what is the best analysis I need to run based on my goal. So we've been talking today about regressions, so automatically I would say I want to predict an outcome. So it goes down the decision tree, and as we discussed, the type of regression is based on your level of measurement for your dependent variable. So say we pick a scale dependent variable, it's going to go down the decision tree and highlight what variable or what analysis you need to run with your specific variables. If you have a dichotomous outcome, it would be a binary logistic. If you have more than 2 levels, a multinomial logistic, and an ordinal dependent variable, ordinal logistic. Okay, so this is a pretty useful tool at the methodology phase. We also have data analysis plans here. This is typically a section that would go in your methodology chapter. If you go to regressions, we have 5 different types. So say you're doing a linear regression. This section is going to break down, hypothetically, what does your research question need to look like, along with hypotheses. And then it breaks down all the different components of a regression model, what assumptions should be checked, along with references, what is the process for interpreting the regression models once you're crunching the numbers, and so forth. So we have all 5 here. I'm kind of focusing on regressions today, but this software does every major statistical analysis. From correlations, you can see all the different possibilities, t-tests, ANOVAs, MANOVAs, non-parametric tests, path analysis, such as structural equation modeling and CFAs, and then even mediation and moderation. Okay. Another component of the methodology is figuring out what sample size do you need to ideally run your analysis adequately. So as you can see, we have all the same types of analyses. If you go to regressions and linear regression uses G-Power software, which is a common power analysis tool. This is G-Power. And depending on the inputs you put in here, what effect size are you looking for? What is your level of significance? How many predictors are you examining? It tells you what sample size you need. So what we have here is a power analysis write-up for a linear regression. Typically, a medium effect size is used for really the social sciences and psychology. For most fields, a medium effect size is used unless you have literature to support using a large effect size or a small effect size for your study. So typically you'll use a medium effect size, and the sample size for a regression is based on the number of predictors that you're using. So as you can see at the top left here, we can change how many predictors we have in our regression equation. So say you had 1 predictor, this is written for 1 predictor, you have 55 people at a minimum is what you would need to target. But you can adjust that up here. Say we had 6 predictors, that is now going to change. The more predictors you have, the larger the sample size requirement. For a logistic regression, you can do a power analysis for a binary logistic regression. So that's if you have a dichotomous outcome, pass and fail, for example. You can do this as well. However, in my experience, the sample sizes are pretty large for a logistic regression. So as you can see here, if you have a small effect size, it goes up to the thousands, which is probably not ideal. So if you go to multinomial logistic regression, I typically use rule of thumbs section I'm highlighting right here. And we have citations to support these decisions. So a rule of thumb is basically saying you need to target a certain number of people per predictor variable in your equation. So if you have, depending on the reference you use, you can kind of tailor it to your needs. If you use the Hosmer citation, then you need 10 people per predictor variable. So if you had 5 predictors, ideally you want 50 people, but he also cautions like targeting 20, that's really more ideal. So 5 predictors times 20, you want to aim for between 50 and 100 people for this example. LeBlanc and Fitzgerald suggest 30 observations. So depending on what reference you use, you can get a range of people that you need to target for your sample size. So now we can go into some examples for interpretation. So I'll run a linear regression first. I have the data sets ready to go. So I'm going to go to analyses down here, and then I'm going to run a linear regression. And in this study, we had a series of variables that measured well-being. So I'm going to see if these subscales predict happiness. So this engagement, perseverance, optimism, and connectedness, does that predict happiness? So in the independent variables box, I have selected those 4 predictors. Our dependent variable is going to be happiness. So you can see the setup of our model here. Under options, we can select what assumptions do we want to check. Okay, so as I mentioned earlier, the key assumptions I typically check are normality with a QQ plot here, homoscedasticity, variance inflation factors are for absence of multicollinearity. You can choose what variable selection method you're using. Outliers, I'm going to disable that, but that can be something you check as well. Usually that's done at the data management stage at the very beginning. And then we'll select options and calculate. Okay, so immediately a full APA write-up is given for this regression. We're testing for assumptions first. So this is the finding of our normal QQ plot. Ideally, you want the data, which represents these hollow circles, you want that to follow this diagonal trend line. And if you hover over it, you can see different possibilities. So it's normal if it follows the diagonal line. It's skewed if it tails off in either direction. And you have discrete data if it's not following the line at all. So maybe your predictor is something like ethnicity. It would look like number 4 here, discrete. Homoscedasticity is checked with a residual scatter plot here. And as I said, you're just making sure that there's no clear trend here. You don't want to see a straight line or exponential curve. You just want to see random scatter. Multicollinearity is making sure that your predictor variables are not highly associated. So here, Intellectus uses variance inflation factors to check for that assumption. And ideally, these values need to be below 10 for the assumption to be met, and that is the case here. So we can proceed with our regression analysis. So interpreting a regression, we're going to go through the 3 bullet point list that we discussed earlier. The first thing you want to do, we can go through the narrative. I think looking at the table really explains everything you need to know. The first thing you want to do is look at the note at the bottom of your table. This is the APA way to present a regression. You want to look at the p-value in this note. Right here, this is the most important step for regression. Do we have a collective significant relationship in the model? Now, as I said, you want to have a p-value below 0.05, ideally. So we're using our f-test, and we're looking at the p-value. Here's the f-test. And then based on that f-test, a p-value is generated. So our p-value is significant. That's good. That means that we have a significant collective relationship between engagement, perseverance, optimism, connectedness, and happiness. Then you interpret the R-squared value. So this is the coefficient of determination. And if you move the decimal over right twice, this is a percentage. So 74% of the variance or change in happiness scores can be explained by these 4 predictors. And then, because step 1 was significant, we have a significant omnibus test. We then go to step 3. We interpret each predictor on its own. So now we dive inside the table and we look across the row of each predictor and we look at the p-value for each of them. So you don't interpret intercept. That's part of the regression equation. You just need to interpret the predictors themselves. So engagement, we go all the way across the row. We can see that this p-value is below 0.05. So we have a significant predictor here. When that is the case, then you interpret your coefficient. So you come back to the second column here, 0.22. And what this means is that with every 1 unit increase in engagement, happiness scores tend to increase by about 0.22 units. That is the trend that we are seeing. The next variable we had is perseverance. That was not significant. We have a p-value greater than 0.05. So you do not interpret your beta coefficient for this. You just stop right here. Optimism was significant. It was a p-value less than 0.001, which is lower than 0.05. But then you come to the second column here, and the coefficient is 0.64. That means as optimism scores increase by 1 unit, happiness scores increase by 0.64 units. Hypothetically, if you had a negative sign here, it just means the opposite. It means you have a decrease in your dependent variable. So if this was negative 0.64, as optimism increases by a point, happiness decreases by 0.64 units. You just say decrease instead of increase. Finally, connectedness was also significant. Similar finding, significant, and it's a positive relationship. As connectedness increases by a unit, happiness increases by 0.28 units. Okay, so that's a linear regression. For this logistic regression, I'm going to do a binary logistic regression here. We need to have a dichotomous outcome for this. So it needs to be just 2 levels. I'm going to use this example here. NCLEX, which is a nursing exam. You can either pass or fail. And we are going to use GPA as our predictor. So we're going to see how does GPA in nursing school predict passing and failing of the NCLEX. Okay, so I'll go to analyses, binary logistic regression. Our dependent variable will be NCLEX, passing and failing. The reference should always be the absence of success or the absence of a condition. I'm going to make the reference fail. The independent variable will be GPA. And then we'll click confirm. We can look at options again, but there aren't many for this. Typically, assumptions are checked for linear regressions more than logistic regressions. Okay, so here is the write-up for a logistic regression. When you have only one predictor in your equation, your p-values are going to match. So you'll have a p-value for your omnibus test, your collective test, and that's going to match the individual predictor's p-value. That happens when you only have one predictor, but as you add more predictors, your omnibus test p-value is not going to match the individual predictors. Okay, so we do have a significant omnibus test, meaning that this regression model appears to be significant. You then interpret the McFadden's R squared. So similar to our previous example, you move this decimal over right twice. So this is 3% of the variance or change in whether a nurse passes or fails the NCLEX can be explained by GPA. It's a relatively small percentage. That means there are probably other factors that attribute to passing and failing the exam, which completely makes sense. Okay, so that's where you kind of have to you have to hypothesize early on in your methodology, what are all the possible factors that could affect my dependent variable? So because we had a significant predictor, we then interpret odds ratio here. It's a little different than the linear regression. We interpret the odds ratio. So that is done right here. And what it means is that with every 1 unit increase in GPA, as GPA increases by 1 point, the odds of passing the NCLEX increase by 350%. So this is, you're changing odds to a percentage, you're just subtracting 100 essentially from this. So that's why it's 350%. You could also say that with every 1 unit increase in GPA, nurses were 4.5 times more likely to pass the NCLEX. It's another way to interpret it. Okay, and then we have a ordinal logistic regression. So for this, you need a ordinal dependent variable. And we have one here. We're going to see whether in this specific location, whether having a degree predicts poverty level, and poverty level wasn't a numeric variable. It's not scale. It's not quite categorical, but it goes up the hierarchy. So low, average, high. This is a ordinal variable. Okay, so we'll go to analyses and ordinal logistic regression. Our dependent variable will be poverty, and our independent variable will be degree. Again, check for options. Then we'll click calculate, and it's going to check for assumptions again. Typically, I just check for multicollinearity for this, but it does do proportional odds if you want that as well. As we come down below, you can see we have a significant omnibus test, meaning that degree appears to predict poverty level. We need to dive into the table more specifically to see what is occurring there. So it's going to have 2 rows depending on how many options there were for poverty. In this case, it was 3 were low, average, and high. It's going to have however many categories minus 1. So in this case, we'll have 2 rows to interpret. So we're trying to see whether in this one, whether degree predicts whether you have having a degree improves poverty level from low to medium or low to average. Then this one's predicting, does it change poverty level from average to high? So this is a rare example where you can have a significant omnibus test. However, the predictors themselves are not significant. This can happen from time to time. And this is going to affect how you write your hypotheses. So maybe you want to disprove that we have a significant omnibus test, that collectively we have a significant regression model. Other times you'll want to dive deep into each predictor on its own and explain what does each predictor contribute to the model. So in this example, you would specify your omnibus test. We do have a significant collective model. However, on their own, having a degree doesn't improve someone in terms of their poverty level. It doesn't help them increase from low to average poverty. And in this example, it doesn't help them increase from medium to high. I just wanted to show you a kind of a specific example there where that can happen. Okay. So that pretty much shows the regression options in Intellectus. We also do have hierarchical regressions. So hierarchical is when you do a regression model in steps. So I can kind of show you that. I'll show you an example of that. Go back to a linear regression. And we'll do a hierarchical linear regression. And we could just put multiple variables in here. Say we put gender in step 1, we'll put engagement and perseverance in step 2, and then optimism and connectedness in step 3. We're trying to predict happiness. What this is doing is it's trying to see if we put variables in sequentially, can you pinpoint what variables are improving the model the most? Okay, so I should have looked at that example. So I guess we don't have enough groups here. So I'll do a different one. We'll do engagement and perseverance. I'm just not going to put in gender this time. Okay, so this is what the model looks like. We did 2 steps. So it's going to check for assumptions twice. It's essentially running 2 regression models. Checking for all the assumptions, and you'll see down here, it's going to put your predictors in steps. So first I said I want to look at engagement and perseverance, and then I want to add optimism and connectedness to the model afterwards and see how much the model improves by adding it sequentially like this. So the key thing you want to look at in this model is how the R-squared changes between steps. So the R-squared was 33% when we only had engagement and perseverance predicting happiness. But once I added optimism and connectedness, that R-squared improved 0.74. So it went up 41%. So that's the key thing for a hierarchical regression, is seeing how the R-squared changes. Okay, so I do want to discuss, we do these consulting sessions on Intellectus statistics. It's a great deal. For $99 a month, every day of the week, we do a consulting session. We have up to 6 participants per day. So during these sessions, we have a specialist here who will help you with your project, answer any questions you have about what type of analysis you probably need to run, how can you clean your data so it's ready for analysis, and they'll also help you with interpretation. So if you need help understanding what the findings mean so you can convey it to your committee, that is something we also provide. Okay, so let me go back to the PowerPoint, and we were around here. That really concludes the session for today. So the key idea here is that if you're trying to predict an outcome, then a regression model is probably your best tool. So prediction is the key word here. You need to determine what method of a regression is best, depending on the level of measurement for your criterion variable. So continuous data would be linear, nominal would be a multinomial or binary logistic regression, and an ordinal dependent variable would be an ordinal logistic regression. Then you need to verify whether your assumptions are met. Follow the 3 steps for interpreting a regression. So look for a significant omnibus test, interpret your R² values, and if step 1 was significant, then interpret each predictor on its own. And then you can use intellective statistics to analyze your data and present interpretations. Okay, that concludes our webinar today. Just to reiterate that Statistics Solutions provides assistance with every part of the dissertation. So we focus today on analysis more, but we help with the literature review, the methodology, journal publications, IRB. We'll assign a specialist to you to help where you need the most assistance. So give us a call at 727-442-4290, or you can email us at info@statisticsolutions.com. All right, so I will now open up for questions if we have any. I think Isaides answered a few questions already. If anyone has additional questions, please type them into the chat box. Okay, I do see a question from Diana. Okay, her question is, I'm using 1 independent variable, anxiety scores, and 2 dependent variables, grades and GPA. Would I use an ordinal logistic regression or a linear regression? So that depends completely on the level of measurement for grades and GPA. So you had 2 dependent variables. You automatically need to run 2 regressions at that point. It's the number of regressions is dependent on the number of dependent variables you have. So you'll need to run 1 model predicting anxiety on LAL grades, and then 1 regression between anxiety and GPA. So if grades are a specific numeric value, like it can range from 1 to 100, you probably would do a linear regression in that example. GPA is also, if it's going to be specific, like specifically like 3.2, 2.5, if you're getting that specific with their GPA, you would do a linear regression as well. Does that make sense? I suppose the alternative is if the grades are multiple choice. So if it's like A, B, C, D, F, then you would potentially do a ordinal logistic regression. But if it's numeric, you would do a linear. Okay. Yep. So if it's numeric, you would do a linear regression. We have another question here. Do you have support for classes or tutoring? Yes, we do provide assistance on an hourly basis. So depending on where you need assistance, we can assign a specialist to you, and we can do tutoring one-on-one, and we can do a screen share, look at your project together, and help address any questions you have. We will be sending everyone a copy of the PowerPoint following the session. Do we have any additional questions? Oh, I just saw another question. I'm not sure if this was answered already. Do we count predictors as dependent variables to calculate sample size? No. When you do a power analysis, you typically only count the predictors. You count what are your independent variables. Does that make sense? When you do a power analysis, only independent variables matter for the calculation, not the dependent. All right, I'll stay on for a couple more minutes. If we have any additional questions, let us know, okay? Thank you, Carly. Thanks for joining us. Yep, have a great night, Diana. We have a question from McDonald asking, at which point in the study design stage do you decide to include a correction test, such as Bonferroni? That's a great question. That would be at the methodology phase. You want to pinpoint that decision as early as possible. So for people who are not aware, a Bonferroni correction is used when you're running the same test multiple times with different variables potentially. What you have to do in those cases is reduce your alpha level. So if say you're doing 5 t-tests with the same dependent variable, typically, you would take your conventional alpha level of 0.05 and divide it by the number of tests that you're doing that are similar. So that would be 0.05 divided by 5 is 0.01 in that example. So that's typically done early on. You need to know after your methodology chapter, are you doing a Bonferroni correction or not? And what p-value are you aiming for in the results chapter? Personally, I avoid doing Bonferroni corrections. It makes it more difficult to prove significance, for one thing, but depending on what reference you read, you're going to get different results. You know, some people will say, if you're doing 10 t-tests, but they're all using different variables, you still need to do a Bonferroni correction. Some people will say you have to be using the same variables to do a Bonferroni correction. So there's a lot of inconsistency in when to use it. So I tend to avoid it unless a committee has asked for a Bonferroni correction. Does that answer your question? All right, great. Looks like we still have some questions coming in, so I'll stay on for a couple more minutes. Any final questions? All right, well, thank you for joining us, everyone. We do 8 of these webinars every month. So we have 4 specialists. We do, I'm going to be doing this webinar again. So we do them twice every month. So if you can't join one day, try to register for the next one. We do a variety of topics. So some are about the literature review, some are about qualitative methodologies and results chapters, and others are about quantitative methodologies and results chapters. So come join us again and let us know if you have any questions. Have a great evening.